Okay, so welcome to the last session of today. For the last session, we have 3 speakers. Before we start, I would like to express my gratitude to the organizers of the conference, especially Ahmed. It's a wonderful, wonderful conference, and look forward to further talks as well. So our first speaker for the last session is Lara Anderson.
Thank you very much. I'd like to echo Kumran in saying thank you to the organizers for the opportunity to be here and for putting together a really interesting conference in a really beautiful place. So thank you very much. As it says on the slides, I'm going to be talking about compactifications of string theory down to 4 dimensions. And I'm interested in particularly theories with n=1 supersymmetry, and I'm going to be studying geometric transitions. So to begin, I'd like to try and motivate why the topic that I'm studying is of some interest, I hope, to the broader community. This is a very wide conference, so yeah, we'll try and see why this is worth the trip. So to begin with, we observe that 4D n=1 theories that arise from string dimensional reduction, string compactifications, come from many topologically distinct geometries. So for example, starting with 10-dimensional string theories and reducing 6 dimensions down to 4, there are many choices for those compact geometries. And of course, if you're interested in categorizing what effective theories can arise from string theory, then the question of which field theories can you obtain in diverse dimensions, in this case 4, is very much linked to the question of which geometries can appear within string compactifications. Now, of course, we don't know the answer to that question in general. The question of whether the set of geometries with a particular amount of supersymmetry is bounded. How do we classify what geometry? And here I'm going to be explaining what I mean by this, but in the n=1 context, we're not just interested in a compactification manifold. We have to decorate that manifold with other structure, like branes, gauge fields, fluxes. So how do we characterize what combinations of that information matters to the 4D effective theory? And I'll explain what I mean by matters in the course of this talk. And then another question that I'm interested in is it possible to dynamically change this topology? So start with one compactification manifold, change to another. How do we describe that both geometrically and field theoretically? So the goal here is to understand geometric transitions, geometry changing transitions in the context of n=1, and specifically I'm interested in n=1 4-dimensional theories. So just to review, I'm going to start with an arena that is the most well-studied in string compactifications. That's Calabi-Yau threefolds. These are 6 real-dimensional compact manifolds with SU3 holonomy. And there are 2 types of geometric transitions that have been very well-studied over the last 30 years. These are so-called conifold and flop transitions, which take you between topologically distinct Calabi-Yaus. So the story here is that if you have a smooth manifold that develops a singularity, in this case, the little spike, there are 2 ways in this context to try and repair that singularity. You can deform in the complex structure of the manifold to smooth out the manifold, in this case by adding an S3 to this singular point, or you can perform what's called a small resolution, which maintains the Ricci flatness property of the compact directions and replaces that singularity with an S2. This gives you a collection of geometries that are related. That's schematically shown here. So if you start with the singular geometry, the spike, then the deformation side is linked to that singularity, and you end up by choosing orientations of this S2 with 2 different small resolutions that you can perform. The conifold transition takes you from XD to either of what I've labeled with an R subscript here, and the flop transition takes you between 2 resolutions by changing the form of this S2. At the level of the Calabi-Yau geometry, this was very well studied, again, many years ago. And it was also, importantly, field theoretically studied very well, starting in the 90s by Strominger, Green-Morrison, and many others. So in the context of vacuum branch change, which I'll talk more about in a moment, in the context of type 2 theories, this type of geometric singularity was a very prototypical example of vacuum change in string theory. We heard talks yesterday that talked about the Higgs and Coulomb branch of the theory, topological string theory. All of that was sort of begun by analysis of this type. Another reason that we might be interested in these types of singularize your manifold and then repair it is that it allows us to connect topologically distinct Calabi-Yaus. And here, this is the famous Kreutzer-Skarka plot of topological integers, the Hodge numbers of the bulk of Calabi-Yau threefolds that we know about. And importantly, to move between dots in this diagram, it is known in practice that you can move between basically any 2 of the dots in this diagram by geometric transitions, and indeed conjectured that this can be done much more widely independent of construction for Calabi-Yau threefolds. So Reed's fantasy and conjecture says that indeed these geometric transitions should connect all Calabi-Yau manifolds, and perhaps more generally, not just Calabi-Yau, but sort of all supersymmetry preserving solutions of string theory, geometric solutions, including SU3 structure manifolds. The nature of how you perform this geometric transition, so how do you change the topology starting at any given point, is very key for all current mathematical efforts to try and bound the number of SU3 structure manifolds. And more generally, these topology changing transitions touch a wide array of questions in string theory. So these are sort of a playground for studying metrics, for studying T-dualities, for studying mirror symmetry, in both the gauge gravity and string compactification settings. There's been a huge amount of interest in these types of singularities. So let me mention one specific reason that these are of interest, again, moving towards 4D n equals 1. So these types of geometric transitions also sort of give you a window into what I'm going to refer to as geometric redundancy. What do I mean by that? I mean that in many contexts, there's more than one geometry that can lead to the same effective field theory in string theory. So different solutions, or different apparent geometric solutions are actually the same physics. Of course, the classic example is mirror symmetry. That's the interchange for the Calabi-Yaus across the axis of this diagram. Here, type 2b and type 2a equivalent on different Calabi-Yau compactifications. Another example of an equivalence happens in either type 2a or type 2b. For example, in type 2b flops, moving across the different small resolutions of the manifold that I introduced earlier, this is producing equivalent effective theories if we allow ourselves to analytically continue into negative Kähler directions. So a little bit more specifically, you have a geometric singularity, but it is possible, due to the structure of Kähler axions of the type 2b theory, to bypass that singularity in a broader field space. So there are theories that can be equivalent because although the manifold goes singular, the full effective theory does not. In this case, here if you have the Kähler axion turned on, this is moving on this smooth plane. And in this diagram, if we set everything to 0, that's the singularity. In both these cases, mirror symmetry or type 2 flops, we again get equivalent physics. So these are examples of, as I've already mentioned, dualities, branch changes, et cetera. So this is one of the reasons that we would like to study these geometric transitions, to understand how different can the effective physics look from 4D compactifications, and also to understand branch changes in a more general context. So the key questions for this talk: are there phenomena like mirror symmetry or smooth geometric transitions in the context of n equals 1 compactifications? What I mean by smooth here is a situation where the geometry can become singular, but the effective physics allows you to change in a smooth way between two different compactification geometries. Can we fully characterize what geometry matters in the n equals 1 compactifications, i.e., for which combinations of background information will I get the same physics? What can I toggle, and how will that change the effective theory? And of course, importantly, because we have many, many possible solutions in the context of 4D n equals 1, can we understand this redundancy more systematically? So that is the goal. This is, of course, much harder in the n equals 1 context than the n equals 2 for a variety of reasons. Primary among them is, of course, that n equals 1 supersymmetry gives us less restrictive information about the form of the effective theory. And indeed, we don't even have a proper notion of moduli space in this case because there's a non-trivial superpotential in the 4D theory. And of course, we're also geometrically doing a more complicated problem. We're not just talking about how a manifold changes its topology. We also have to talk about other structure and how that plays with these types of geometric transitions. So specifically, how bundles, branes, and fluxes travel across these transitions. So this is the goal. Let me give a sort of brief illustration in the context of heterotic string compactifications for why the other stuff plus manifold matters a lot. So conifolds in the n equals 1 context, in heterotic string theory, we cannot just say, I'd like to ignore that other data of the background. So in the context of heterotic, we have not just a Calabi-Yau manifold, but also non-trivial gauge fields that live over that in background, i.e. holomorphic slope-stable vector bundles. We could say, let me just turn off the bundle and perform the geometric transition that I want anyway, but of course you can't do that because of anomaly cancellation and the non-trivial Bianchi identity of the theory. Specifically, there's a 3-form, and it requires from the anomaly cancellation that this condition here must be satisfied. that you must balance at the level of Chern classes. The curvature, the second Chern class of the manifold has to balance the second Chern class of a holomorphic vector bundle. All of this is just to say that the anomalies tell you you can't turn off the gauge fields. They have to play a role in what's to happen next. Here I've illustrated this condition written in terms of field strength of a vector bundle, but you can also make the same story with NS5 branes and the heterotic compactification. And again, you need non-trivial gauge sector, whether that is a brane or a bundle, in order to satisfy anomalies. So just to summarize, this means we can't set the gauge fields to 0, and you need to understand how the change in the bundle is going to compensate in geometric transition in addition to the Calabi-Yau geometry itself. So this is a primary geometric mathematical reason why this has not been as well studied or understood in the context of n=1 solutions as it has for just pure Calabi-Yau manifolds or type 2a, type 2b. So the motivation of this work is trying to understand what happens to the gauge fields in heterotic, and the question you want to ask is, where could you start? So motivated by this question of redundancy and can I get the same effective physics, my collaborators and I decided to start with examples where the effective physics seemed to be looking very much the same across a geometric transition in the context of a heterotic compactification. So there are examples observed of n=1 redundancy not descended from n=2 solutions. Examples of this arose in the heterotic context in which you have distinct geometric systems, so geometric backgrounds. These are pairs of some Calabi-Yau manifold X, and, oh, that's a typo, that should be V over X, a holomorphic vector bundle that lives over it, that lead to the same, at least massless spectrum in the 4D theory. Examples of this arose in the context of 0-2 gauge linear sigma models, and this went under the name of something called 0-2 target space duality, which I won't get into today, but it was basically the observation that certain 0-2 theories could share a non-geometric phase. So they're not the same 0-2 theory. There's no reason to believe that they were isomorphic or leading to the same physics. However, it was observed that for certain solutions that shared a non-geometric phase, the spectrum turned out to be the same. The observation, which was not, again, obvious from the GLSM, is that the base Calabi-Yau manifolds in these examples are generically related by conifold transitions. So this struck us as an interesting arena to begin with examples where we could see that perhaps the physics wasn't changing a lot across a geometric transition. So here's a specific example of two Calabi-Yau manifolds. I've called them XD for deformation and R for resolution. This is the classic quintic conifold, one of the first ones that was worked out in the n=2 context. And again, we're going to start with one manifold that is singular. Imagine starting in the middle with spikes. We can perform a change in complex structure to smooth out the manifold, or we can replace those singularities with two spheres. That's the small resolution. I'm not going to get into the details of this, but there are explicit vector bundles. In this case, a very simple solution, which is a holomorphic deformation of the tangent bundle, about as easy as you can get for a vector bundle to start with. And we're going to argue that this gets carried through across the geometric transition to something on the other side. So here's a specific example. Here's the structure that one could observe about that example that might be intriguing and require an explanation. What happens to the degrees of freedom of the theory for an example like this? So you have a base manifold that's connected by a conifold. Here, the Hodge numbers that tell you about the topological integers associated with the manifold. For the quintic, the famous 101. And in this case, I have certain degrees of freedom that correspond to fluctuations of the gauge field. This is the vector bundle moduli. On the resolution side, you have a different set of integers for all the pieces, but the total on both sides happens to be the same. Also, I didn't write it here, but in this particular example, you have an SO10 4D gauge theory, and you have charged matter under it, massless charged matter, which also agrees in terms of its dimensionality. OK, so with my collaborators at Virginia Tech, James Gray and Callum Brody, we pulled apart the geometry of examples like these, and we developed more general rules for how a bundle must adjust across a conifold to maintain a consistent heterotic theory. A bit more strongly than consistent, we were interested in cases where the spectrum is going to be the same. The reason we're interested in examples like this is that we're interested in, like in the n=2 flop context, this seems to be a minimal change in the physics as you move across the singularity. So we wanted to understand first the geometry and then, of course, what's happening physically after that. This contains examples of this that I mentioned, the 0-2 target space duality, but it's much more general. And importantly, as I'll talk about if I get time at the end, it can be applied to other classes of n=1 compactifications. So for example, type 1, type 2b orientifolds, F theory, et cetera. So for concreteness, I'm going to give an overview in the context of heterotic compactifications, and I may speak briefly about these other solutions towards the end. So explicitly, here's a bit of geometry that we have to discuss. you can ask, how does the manifold and its holomorphic tangent bundle change under geometric transition? This was known, again, for many years, how the Hodge numbers adjust across a conifold. We also were looking at how the second Chern class or character adjusts across a conifold transition and observed this structure. And importantly, we looked at the holomorphic cotangent bundle and observed that the relationship between deformation and resolution side had a particular form in terms of a short exact sequence of this type. The mathematical details of this are not important. However, this looked very familiar for people who had worked in the context of heterotic compactifications. This looks like something that arises in the structure of a so-called small instanton transition, or more mathematically, something called a Hee-Cheol transform. So what's the idea behind that? The way that these cotangent bundles appear to be changing is linked to a structure in heterotic in which you have heterotic compactifications, in which you have an NS fibrane that can be either absorbed or emitted from the gauge fields that live over the Calabi-Yau. So if you have a localized source, like an NS fibrane wrapping a curve inside the manifold, it is possible to smooth that out into a solution that is a consistent gauge bundle, and vice versa to, in certain contexts, to collapse and pull off again. So the way that the geometries are aligning in the form of a conifold looks something like a small instanton transition. Why is that significant? Because this is telling us in a very specific way how the cotangent bundles are adjusting across a conifold. And then you can ask, what do I have to do to the gauge bundles in order to sort of compensate for that change? So a bit more specifically, recall the anomaly cancellation condition that I introduced earlier in the heterotic context, the balancing of second Chern classes that has to adjust for manifold and gauge fields. You can ask, how does this change during a geometric transition, as I was just mentioning? So basically, the structure of that change in C2 on the resolution side says that to move from resolution to deformation, you have to introduce the class of the CP1s, i.e. these S2s that I'm introducing in a small resolution. In order to keep anomalies canceled, this also has to appear on the other side. So this gives you something of a hint of how the gauge bundles have to adjust. On the next slide, I'm going to sort of show you that adjustment at the level of classes or topology, just simply written for clarity, and all of the sequences of sheaves required for this process to occur to exist and can be written down explicitly. All I'm saying is that we can understand how to sort of pull apart and put back together gauge fields across this geometric transition. I'm sorry for my weird formatting here. And what follows, this thing which you can't read, is a V sub S, is a spectator bundle which goes through the transition in a relatively trivial manner. So here's the story. I begin on the resolution side, and I satisfy anomalies. I understand that in order to move to the deformation side, effectively I have to add something that's appearing with a negative sign in the components of the gravitational sector and a positive sign in the components in the gauge sector, i.e. I have to add positive and negative charge across this anomaly cancellation condition in order to produce a consistent thing. So here, I've added the class of the P1s, I perform a small instanton transition in the cotangent bundle, and that's taking me to something that's approaching the deformation side. It's at least at the singular, it has the topology of the singular limit. If you were able to perform a small instanton transition in the gauge fields, this would do the same thing. However, in general, you can show that you can't actually absorb these P1 classes as a fibrane into the resolution gauge fields in play. Instead, it is only possible to do this for the examples that we looked at in the case that you have special substructure in the bundle, specifically if you have a particular curve that can lead to an NS fibrane, or be wrapped by an NS fibrane, that appears inside the geometry. I've called this CR. In this case, it's possible to actually combine this curve with the P1s, to recombine it, and then end up down here at a situation where you now have the appropriate topology to be on the deformation side. You can smooth this out and end up at a consistent geometry on the deformation side. So that was a lot of words, and I haven't given you the details for that. What is it that I want you to take away from this slide? At the level of charges, all you're doing in the conifold is adding and subtracting quantities across your anomaly condition. And then in terms of how you can recombine geometric objects, there's something particular that we notice as structure, and I'm going to circle it here. These curves that I've called CR and CD, if these appear in the geometry, then we could show geometrically that the spectrum is going to be the same across, for the heterotic effective theory, is going to be the same across the geometric transition. So we can boil down the what's happening here and what is the physics of interest to these objects right here. So thank you. We have called these bridging branes.
And the spectrum matching that we find in the heterotic case is based on the properties of special space-time filling NS5 branes that wrap curves on either side of the deformation and resolution, and they're linked to the conifold pair. Here's the geometric property that seems to play a crucial role. These are curves in, for example, CR is a curve in XR which do not collapse in the conifold, but they intersect the collapsing cycles. So basically, you can have things that, as a cycle collapses to 0, they go away. You can have things that never touch it and don't care about the singularity, and then one other class which are talking to that singular limit, but they themselves are not collapsing. If you look at just the pure five-brane theory then, so strip away the vector bundle and say, I'm just looking at NS5 branes, you can ask, what are the degrees of freedom of that theory? And the massless spectrum is counted by these cohomology groups. For bridging curves, you can show that this bundle or curve moduli adjusts across the conifold to exactly compensate for the change in Hodge numbers, and we can prescribe what these curves are for any conifold pair. So every conifold gives you a pair of curves of this type, and if they are present in the background, then your spectrum is going to match. So what is happening with that? These pure five-brane heterotic theories are identical, and for Calabi-Yau threefolds with these bridging branes, they correspond in a description. If you were to write both the deformation and resolution as complete intersection descriptions in the same ambient space, it turns out that the bridging curves themselves are actually the intersection of the deformation and resolution sides of the geometry intersecting in some bigger ambient space. The general heterotic conifold duality induced from this, and here I'm using the word duality loosely, at this moment only matching spectrum. These are sort of the general properties when these curves exist. These are giving you all of the structure of the theory that is going to match, so the massless spectrum, and I'll show you more. If these branes are present, then by small instanton transitions, you can also generalize them to bundles. And in each case, the full heterotic theory is going to give you the same spectrum and perhaps be identical. So we observe correlated geometry and matching massless spectra. We want to ask, is this a true duality? Are we seeing something deeper? Or are we having distinct theories with intersecting vacuum spaces? Can we use the geometry of these bridging branes and other string compactifications? Now, I have only a short bit of time, so I'm not going to go through all the details of this, but I'm just going to introduce some of the tools that we use to try and answer this question and what evidence we have for whether we're uncovering new n=1 dualities or simply vacuum change. So I'm going to illustrate this for the case of pure NS5 brane heterotic theories. Remember that in something like Calabi-Yau mirror symmetry, you understand that you're interchanging Hodge numbers or complex structure versus Kähler degrees of freedom in the theory. And the question here in a pure five-brane heterotic theory is what is happening to the degrees of freedom that correspond to the manifolds in NS5 branes? How are they being rearranged across this purported duality? This can be generalized to bundles directly. I'm not going to go through that. This is hard to do directly in terms of finding a field mapping in a 4D n=1 theory, because of course we don't fully know a lot of aspects of that 4D theory. For example, the n=1 Kähler potential is not known in general. But there are tools that you can use to attack it. So the full geometries, manifold plus brane, have to meet in the middle at the conifold locus. And the geometric degrees of freedom live in intricate equivalence classes, and you have to map physical to physical degrees of freedom. So that turns out to be very restrictive in terms of understanding what the purported moduli map would be in this case. So the very rough idea in 3 minutes or less is here I've given a geometric system corresponding to two equations that provide a Calabi-Yau manifold. Here the subscript 1, 3, and 0, 5 are the weights in a particular toric ambient space. And then two equations that produce a curve inside that Calabi-Yau threefold. This is a brane. The details of this are not important, except to note that the overall degrees here of 1, 3, 0, 5, 1, 4, 1, 4, across a conifold end up being interchanged. So we end up with a resolution side geometry in which the degrees of the defining equations are the same as the degrees of the brane on one side. It's turning into manifold on the other. And the degrees of the manifold on one side appear to be the same polynomial degrees as those of the brane on the other. This is, again, the feature that the curves are the intersection of these two geometries in some shared ambient space. So if you want to map degrees of freedom, it's tempting to interchange brane and manifold defining equations. This is not possible in general, and since Kumran is giving me you're almost out of time, I'm not going to go through the details of why this doesn't quite work. But it turns out, again, because of this geometric equivalence classes and structure, that isn't quite the right moduli mapping. However, we can find one, and just to show you there's a calculation to be done, here's the structure of certain geometric equivalence classes that arise to describe the fluctuations of a manifold in a five-brane. So these are the objects that you have to match. And here's the punchline of what we find. So I'm going to skip this part. What we find is that we have a purported mapping. We can map all the degrees of freedom. Let me just summarize this very briefly. Across a conifold, for example, the quintic, we find that in this 5-brane system, 86 complex structure degrees of freedom move across to complex structure, but 14 of them turn into brane moduli, and interestingly, 1 complex structure moves into a Kähler modulus. If you're familiar with the structure of n=1 theories, this is a weird structure to be seeing. The Kähler and complex structure moduli enter the theory in very different ways, so there's something very non-trivial to be tested here. So here's what we want to now ask. We want to explore whether the theories, not just their spectra, are identical, and so we need this mapping of fields to do it. So we have provided a purported test of how the moduli should map based on geometry. Now we want to test it on the effective theory. So here's where we've gotten to on that. We can take examples of pieces of the heterotic theory that we understand very well. So for example, the holomorphic superpotential is something that we can compute in detail. And in this context, for example, if I had an E6 theory, I can compute something like a 27-cubed coupling and ask, does this match now with the moduli mapping that we have induced from the geometry? You can also look at non-perturbative contributions to the superpotential and ask, can these obstruct the transition? Do you find agreement? So since I'm out of time, here's an explicit example of geometry where we tested this. And the punchline of that calculation is that in examples, this one in particular, we find that there's roughly 140,000 independent holomorphic functions in the superpotential that match exactly. So this is strong evidence that what we're looking at isn't just a geometric fluke. This isn't just vacuum spaces that are intersecting. This is looking like the same effective physics at a deeper sense. More generally, for non-perturbative contributions to the superpotential, we can compute sums of contributions to the superpotential that do not have to vanish by Beasley-Witten vanishing, and argue, will they be 0 or not? There are some that are not forced to be 0 by Beasley-Witten, but actually prove to be 0 anyway, including ones of this type that might obstruct the transition. So these actually vanish, and the remaining non-perturbative terms have non-trivial matching of Pfaffian prefactors and moduli dependence. So long story short, the effective physics is looking very much the same. So I talked about this in heterotic. I'm not going to go over this today, but if you're interested, ask me. There's many other contexts you can try out this type of geometric construction. So most of what I've talked about is only Calabi-Yau geometry and the structure of curves or branes inside it, not intrinsic to the heterotic context. And we have now examples in type 2b orientifolds in which we see the same structure. So here's an example of a type 2b orientifold that I won't talk about. Instead, with my last 1 minute, let me just try and summarize why all this geometry and discussion was worth the trip, hopefully. We seem to have evidence that there are new and intrinsically n=1 dualities. Now, I have not talked about what the physics of that transition might be, and this is something we're actively working on. Happy to discuss ideas afterwards, work in progress. But it is potentially interesting that we find, not like in mirror symmetry where you have pairs of theories, but long chains of them. So you can connect very many geometries by geometric transitions explicitly. And this is of clear relevance, for example, if you're doing model building, scanning over possible heterotic constructions or type 2b constructions. For the computation of the effective theory, this is also extremely powerful because you have large redundancy of theories, and you can have a different geometric arena to try and tackle the same quantities, to compute the same quantities. More on that, this is a potentially powerful embedding in that it gives you theories in which you have a low number of Kähler moduli, and you can import information to high H11. That's potentially very simplifying. We also have a better idea, thanks to this analysis, about what type of geometry matters for the effective physics. So it would be nice to be able to say, if you hand me two n=1 geometric solutions, when are they going to give you the same physics? That's not something that we've been able to answer, and we're moving closer to that now. Work to appear, ask me if curious. You can ask, does this have to be Calabi-Yau threefolds? What about Calabi-Yau fourfolds and F-theory? And there is an analog of that story there. And then, of course, the very important question, which I didn't have time to get into and we haven't fully understood yet, is what is the physical transition? And is this like in type 2b flops? Is there a way to bypass these geometric singularities in the n=1 context? So could the presence of these bridging branes lift electrolyte states from branes wrapping collapsing cycles? We seem to say that there's evidence that that's the case, but this is something we're actively exploring. So with that, since I'm over time, I will stop, and thank you for your patience.
Any questions for Lara?
So you just said it on the previous slide, maybe, but did you also say that you observe these generalized conifold transitions in the type 1 compactifications as well?
Yes. So type 1 goes through very similarly. Again, you have NS fibranes. You can sort of, the way that they enter the massless spectra of the theory is very similar to in heterotic, also SO32. The way it happens in type 2b orientifolds is very different, but again, the structure plays the same role. So
Same anomaly matching.
anomaly matching charge, balancing charges, and then tracking this geometry across, you end up with theories with the same massless spectrum and apparently same physics. So there's something to be explained at the level of sort of basic brain physics across any of these contexts.
Very nice talk, Lara. Well, this is totally new from n equals to 1. No? There's no an unlock of this for n equals to 2 or anything.
No, because in order to, the interchanges that we're playing with are really mixing information about geometry into other structures, like in this case, the degrees of freedom of an S5 brane or a vector bundle. In F theory, this is about mixing flux into manifold. So it's not something that you can see when the only geometric input is the manifold. It's something that is definitely more than that.
Even just type 2b with the orientifold, which we don't see.
I mean, in order well, type 2b with an orientifold, right, to really cancel charges, you need a brane to balance your orientifold charge. So then once you put that in, then you're in the context we're talking about here.
And just a curiosity, in the case that you had the superpotentials to vanish to match the duality, do you understand why those superpotentials are 0? Is there any symmetry or something behind?
It's a great question. I understand mathematically, like I can sort of, prove why certain, Pfaffian prefactors are summing to 0. At a level of a symmetry explanation, no. We are interested, so there are some terms that do involve this sort of new Kähler modulus turning into complex structure, which don't vanish, and that gives you a really intricate set of conditions on the moduli for how these theories are going to agree, which does seem to work. But again, this is the question of, what is the deeper physical explanation, which, yeah, we don't have the full story in yet.
Okay, thank you.
Any other questions for Lara? If not, let's thank Lara again for a beautiful talk. So our next speaker is Hee-Cheol Kim. There you go.
Okay, first of all, thank you very much for the invitation. So today I'll be talking about finite landscape of 61-0 supergravity. So this talk is based on my recent paper with Kumnoon here and also Kaizu at Harvard University. So let me start with the motivation for this work. So in all the examples we know from string theory, number of string vector in Minkowski space is finite. And also, Yau conjectured that number of Calabian manifolds in each dimension is finite. So this may imply that number of string vector indeed may be finite. And these ideas naturally lead to the finiteness conjecture proposed by Buffer and Acharo and Douglas. We claim that the set of consistent quantum gravity vector is finite. And also related claim is that number of massless fields in gravitational theories has upper bound. So, for example, the infinite families of theories are not allowed with gravity. And these finiteness conjectures are well established for the theories with the largest supersymmetry. For example, the theories with 32 Suji, as we know, they are uniquely determined by supersymmetry. So they are essentially toroidal compactification of M theory or type 2b theory. So the finiteness in this case is trivially satisfied. For the 16 supersymmetry case, we can use unitarity of string proofs or some Swampland conjectures to show that number of quantum gravity theories is also finite. In fact, the rank of gauge algebra is bounded by 26 minus d for the given dimension d, as discussed in this paper. So for example, in 4D, n equal 4 super Yang-Mills cannot consistently couple to 4-dimensional gravity if rank is bigger than 22. Of course, this doesn't mean that we cannot engineer gravitational theories containing this 4D n equal 4 super Yang-Mills, but it just means that this 4D theory cannot consistently couple to the 4-dimensional gravity. So gravitational theories are really different from the ordinary field theories without gravity. This also brings us to the related conjecture called the string Lamport principle or string universality. So it claimed that all consistent quantum gravity theories arise from string theory. So it means that quantum gravity theory, as quantum gravity landscape, exactly agrees with the string landscape. So again, for the theories with large number of supersymmetry, this conjecture holds very nicely. So for example, in 10 dimensions with 16 supercharges, as we know, gauge groups are fixed by gauge anomaly cancellation conditions. So the only allowed gauge algebras are the following four. And the first two gauge groups has a string theory realization, but on the other hand, in the latter two gauge groups containing abelian factors doesn't have realization in string theory. But recently, it was shown that these two theories indeed, these two gauge groups are indeed inconsistent when coupled to gravity. Therefore, in 10 dimensions, string Lamport's principle hold with 16 supercharges and also 32 supercharges. In lower dimensions, however, it's not easy to show this principle hold, but there are many papers discussing such principles in 90s and 80s, and they showed that string Lamport's principle hold in 90 and 80. But we still need to investigate lower dimensional theories. Then the natural next question would be, can we establish finiteness conjecture and string universality for the theories with 8 supercharges? So as we all know, this is a highly challenging question to answer, but today I'll provide very strong evidence supporting these conjectures. So for this, I'll focus on 6-dimensional 1,0 supergravity in Minkowski space. So these theories are special with several reasons. First, 60 is the highest dimension with 8 supercharges, and these are chiral theories. Therefore, anomaly cancellations provide very strong restrictions on the structure of these theories. And furthermore, there is a proof in math by Mark Gross saying that the number of elliptical labia threefold is finite. So this means that finiteness conjecture holds at least for 60 F-theory models. However, there are infinite families of anomaly-free supergravity theories discovered in these papers, although some of them are ruled out by using unitarity of string theory, but still we have many more infinite families. So it's unclear whether such finiteness conjecture hold in 6 dimensions with 8 supercharges. So regarding this question, today I'll provide a bottom-up argument that shows that number of massless fields in 61 supergravity has a upper bound, and the theories saturating this bound are realized in string theory. So here, to argue this, we will use 2 assumptions. So our first assumption is that we have tensionless BPS strings at every point on the tensor moduli space. And our second assumption is that classification of SCFTs and little string theories, which are extensively studied in these main papers, is complete. And all the known string theory examples are consistent with these 2 assumptions. So I believe these assumptions are reasonable. So based on these 2 assumptions, I will show you kind of finiteness of 61 supergravity theories. So this is my plan for this talk. So I'll first give a brief review on 61 supergravity. Then I'll explain some key properties of the tensor moduli space and BPS strings. Then using these properties, I'll show you how to prove the finiteness of 61 landscape. And lastly, I'll present exact bound we compute on the number of massless field and show you that concrete F-theory models saturate this bound. Okay, let me begin with the introduction to 1 supergravity in 6 dimensions. There are 4 types of massless supermultiplet. First one is the gravity multiplet. It contains the graviton and also self-dual two-form field. And in 60, there is a particular multiplet called the tensor multiplet. Each tensor multiplet contains anti-self-dual two-form field and also real scalar field J. And the vacuum expectation of value of this scalar field parameterize the so-called tensor moduli space, which is our main interest in this talk. Furthermore, there are vector and hypermultiplets. And we call the number of tensor and vector and hypermultiplets by T, V, and H, respectively. And there are massless chiral fields in 6 dimensions, such as two-form gauge field and metafermions. They contribute to the gauge and gravitational anomalies. And these anomalies are captured by this one box diagram with 4 external gauge and gravitational sources. And consistency requires that this anomaly must be canceled. But this anomaly doesn't cancel by itself. So in 6 dimensions, we have Green-Schwarz mechanism that cancels this anomaly by introducing this kind of Green-Schwarz term to the action. Then it induces 3-level anomaly like this, mediated by 2-form field. And this anomaly can cancel this one-loop anomaly. If the anomaly polynomial from the one-loop box diagram factorized in the following way. Here, omega is the tensor intersection form with 1T signature, and B0, Bi, which are coefficients in front of R square term and Fi square term. They are called anomaly vectors, and they take the values in R1T space. The conditions for such factorizations are the following, and these conditions are called anomaly cancellation conditions. So every consistent 6D supergravity theory must satisfy all these conditions. So in particular, the first condition is called the gravitational anomaly cancellation condition. It relates the number of hyper and vectors and tensors, which is kind of main ingredient to show the boundedness of the 6D landscape, which I'll explain later. So let me explain the tensor moduli space, which is the T-dimensional coset space of this form, parameterized by the scalar field J in the tensor multiplet. Then the consistency of the effective field theory on the tensor moduli space requires the following inequalities, following positivity condition on this scalar field J, and also anomaly vector Bi and B0 like this. The first condition is to guarantee metric positivity on the tensor moduli space. And then second condition is for the positive gauge coupling for the gauge group Gi related to Bi. And the third condition on this vector B0 can be argued by using consistency of compactification of the theory on a K3 while preserving supersymmetries. But there are more arguments showing this positivity discussed in these papers. In F theory, the scalars correspond to Kähler form on the base, and these positivity conditions are required to define a positive definite Kähler cone on the base. So all the F theory models satisfy these positivity conditions. There are also BPS strings on the tensor moduli space, and their tension, which is proportional to J dot Q, where Q is the charge of the BPS string, must be non-negative. So we have additional positivity condition for every BPS string charge Q. And these strings are half BPS sources for the two-form field, and as I explained, their tension must be non-negative, and their charges must be sitting in the so-called unimodular charge lattice gamma, as discussed by Cyborg and Taylor. And these charges form a cone called BPS cone, and this cone is dual to tensor cone, which is the cone of the scalars. And this BPS cone is spanned by generators, which we call CI. So every BPS charge in the BPS cone can be written as a non-negative integral sum of these generators like this, with non-negative integral coefficient here. And we also found that the scalar field, the collection of the scalar field, must be sitting inside the BPS cone due to this J-square positive condition. Therefore, we can rewrite this scalar field in terms of generators with non-negative coefficient. In F theory, BPS cone corresponds to Mori cone, and the tensor cone is the Kähler cone on the base B. A crucial feature of such BPS generators is they are shrinkable, which means that we have BPS strings for each generator, and such a string has a tensionless limit at certain point on the tensor moduli space where J dot Ci equals 0. Since they are shrinkable, they are actually classified in these papers. So they fall into two categories depending on their self-intersection number. Firstly, if the generator, its square is negative, the tensionless limit lies at finite distance. So the generator corresponds to SCFT generator embedded inside the supergravity. When the charge square is 0, the tensionless limit exists at infinite distance. So the generator corresponds to either little string or critical string inside the supergravity. Also, since the generators are all classified, in principle, we know many information about these generators. And so from this information, we can extract non-trivial structure of BPS cone. For example, two distinct generators must intersect non-negatively. And this can be proven by using mixed gauge anomaly cancellation condition and also properties of E string, M string, and critical string. But I'll skip the details. Among many BPS strings, there is the distinguished class of strings, which we call H string, and they play a very important role in our proof of the finiteness. So this H string is the main player in our proof. H string satisfies several conditions. So let's say the charge for the H string is F, then F scale is 0, and B0 F equal 2. And these two conditions imply that H string is related to heterotic string. That's why we call it H string. And also it has a tensionless limit at infinite distance. More precisely, H strings are critical heterotic strings and little strings sharing the same charge class F, satisfying these two conditions. In F theory, they correspond to these three branes wrapping rational fiber curve F on a base. For example, consider an F theory with a base given by Hertzsprung surface Fn with 1 point flow. Then base looks like this. Then here we have a rational fiber curve with self-intersection 0. Then the D3 brane on this curve provide heterotic string theory in the tensionless limit in certain duality frame. On this side, we have another rational fiber, but this time it's formed by two intersecting -1 curves. Then this brane on this curve provide little string, but these two strings share the same rational fiber curve class F, and they both become the tensionless at the same time when the volume of this fiber curve shrink to 0 size. So these two strings are H strings. We can extract more constraint from the central charges of the 2D CFT living on the H string. We compute it using the anomaly inflow, and this is the result. So left-moving central charge of H string is 20, and right-moving central charge is 6. And these central charges agrees with those of the heterotic string indeed. And Ki is the current algebra level for the bulk gauge algebra GI in the 6 dimensions associated to this vector Bi. And level is given by intersection number of F and Bi. So whenever this level is positive, we have the current algebra for the corresponding gauge algebra on the world sheet of this H string. Then using the unitarity of world CFT on the H string, we can extract the following inequality. So every current algebra provides the central charge contribution to the left-moving sector. So their summation must be less than or equal to the total left-moving central charge. In this case, it's 20. And from this inequality, we can get a constraint on the rank of gauge algebra. So for the positive Ki, the rank of the gauge algebra is bounded by 20. So we call this gauge algebra with positive Ki as an external gauge algebra. In this geometric example, for example, this curve and this curve supporting G1 and G2 gauge algebra intersect H string. Therefore, their rank is bounded by 20. Now, I'll show you that every 6D supergravity theory must contain H string in its charge spectrum. To show this, I will use the property of this charge B0. And from the classification, we can read of this intersection of B0 with each generators, and this is the result. And as you see here, only H string and also generator with the self-intersection -1 has positive intersection with B0. And now recall the positivity condition on this anomaly vector B0. As I said, J dot B0 must be non-negative, and also the scalar field can be expressed as a non-negative sum of the generators. So combining all these conditions together, we can now deduce that every supergravity theory must contain either H string or -1 generator, or both. Now I'll define a projection to the subspace of the tensor moduli space, which is orthogonal to all -1 generators. So it's defined in this way, and this is called blowdown. So after blowdown, the BPS cone is also projected to the subspace, but this subspace doesn't contain any -1 generator. But this positivity condition still holds because it holds everywhere on the tensor moduli space. So this positivity condition implies that the theory must contain H string. So this proved the existence of the H string for every 6D supergravity theory, except two cases. So firstly, when t equals 0 case, we don't have tensor moduli space. Therefore, our argument doesn't apply. But second exception is p equals 0 case. In this case, this positivity condition is trivially satisfied. But this can occur only when t equals 9 case. So except these two cases, when t equals 0 and t equals 9, all the other theories must contain H string in each BPS string charge spectrum. The last ingredient for the proof is the containment relation of SCFTs inside the H string. So here we will claim that BPS strings with the charge Q satisfying the following conditions must be element in a little string theory of the charge class F for the H string. So Q here is orthogonal to H string charge F, and also the gauge algebra supported on Q is not the small type. Here, small gauge algebra means no gauge algebra or SU2 spray 4 or SP2 or G2. So if this condition is satisfied, we are claiming that this charge Q and also corresponding tensor multiplet and BPS string must be element of this little string theory of H string class. We can prove this using the following two properties. Firstly, when H string shrinks, which occurs at infinite distance, Q string also shrink. This condition follows from this orthogonality condition. Second condition is that intersections of this charge Q with all null generators are finite if the gauge algebra is not of this small type. I'll not go into details, but using these two properties, we can prove this containment relation. So we'll use this. Now we are ready to prove the finiteness of the number of tensor multiplets. For this, recall the gravitational anomaly cancellation condition. So it said that sum of all gravitational anomaly contribution from every element in the supergravity is 273. But in this paper, there is a very interesting observation. They found that the only component in the gravity theory having negative contribution to the gravitational anomaly are SCFT atoms with charge Q satisfying this self-intersection condition. So Q square is less than, Q square is -5 or less, up to -12. And this charge Q supports exceptional gauge algebras, such as F4, E6, E7, and E8. And all the other components in the gravity theory have a positive contribution to this gravitational anomaly. So to have infinitely large number of tensor multiplets, we need a large number of these atoms. These atoms fall into two categories. Firstly, it can intersect H string. In this case, as I explained, their rank is bounded by 20. In the second case, since they are orthogonal to this H string, these charges must be element of the little string theory. So in this case, we can use the classification of the little string theory to extract the property of these charges. What we found is quite surprising. So classification of the little string tells us that whenever we have these atoms, they are always accompanied by additional methods. So that if we compute the gravitational anomaly contribution from these negatively contributing atoms, together with follow the additional methods, then their total gravitational anomaly contribution eventually become positive. So these two conditions means we cannot have arbitrarily large number of these atoms. So to show this, I have one slide. So we can use the classification of the SCFTs and little string theories, which was done in these papers around 10 years ago. They showed that these theories are actually the generalized Quiver theories with a tensor base given by this. So the tensor base is like tree-shaped diagram. It contains a node and link. And node is nothing but a single tensor multiplet with this self-intersection number. And link is a finite chain of the tensors with this self-intersection number. But important point here is that whenever you have node, you always have one or more links. So they are all connected. So you can find each block, you can divide all the tensors into some blocks containing the node and link. Then each combination we found that they contribute to the gravitational anomaly positively, roughly bigger than or equal to 30. So every building block of the little string theory of H string have a positive contribution to the gravitational anomaly. So together, this shows that number of tensor multiplet in the Schichty supergravity theory is finite. And with a little more effort, you can also show that number of vectors and hypermultiplets are finite, but I'll not explain the details. But together, we establish the finiteness of number of massless fields in Schichty 1-0 supergravity theories. We can go further, actually, and compute the exact bound on the number of tensors and rank of gauge algebras. So our idea is just straightforward. So we can first identify the composition of the atoms for the little string theory in the H string charge class F, such that it can host large number of tensors and higher rank of gauge algebras. Then for the given H string configuration, we can add external methods that intersect H string, such that the resulting supergravity theory contains maximum number of tensors and highest rank of gauge algebras. And this program can be conducted systematically, and we found the following solutions. So the first theory is the T-max theory containing maximum number of tensors. Its base configuration is like this. It contains one little string theory for the H string, and H string consists of 16 EA times EA conformal methods. And this H string in the middle intersected two external tensor multiplets supporting E8 and E8 gauge algebras. In total, they form a complete supergravity. So this theory contains 193 tensor multiplet and this gauge algebra. This theory is the maximum tensor theory we can construct while satisfying our constraint in the Schichty supergravity theory. The second theory is the maximum rank theory. It contains, again, one little string theory for the H string, and the little string base is this affine EA type diagram supporting SO type and also SP type gauge algebras. And this H string intersects one external tensor multiplet with SO32 gauge algebra. In total, we have 9 tensors, and rank of gauge algebra is 480. And these are two theories having maximum tensor and maximum rank, which we can construct in Schichty supergravity. So we found the bound on the number of tensors T, which is bounded by 193, and rank bound is 480. And furthermore, it turns out that these two maximal theories are realized in string theory. They are theories living on 24 instantons on EA times EA, or SO32 heterotic string compactified on K3 with E8 singularity. These theories are studied in these papers. And we also found they are trivial to each other on the circle compactification. Therefore, two maximal theories has concrete realization in string theory. They belong to the string landscape. So this result shows that provide non-trivial evidence for the string Lampos principle for the Schichty 1-0 supergravity theories. Okay, let me summarize. We have shown that Schichty supergravity theory has bound on the number of tensors and rank of gauge algebras. And to show this, we have various consistency conditions on the tensor range and also BPS strings. In particular, we use the classification of Schichty SCFTs and little string theories. And our result also predict very sharp bound on the Hatch numbers of elliptic Calabi-Yau threefold like this. And we also found the threefold saturating this bound can be explicitly constructed by using the base given by Hertzberg surface F12 with blobs and with the specific choice of the fibers. This also provides further evidence for the string Lampos principle. Okay, let me stop here. Thank you very much for your attention.
Any questions for Hee-Cheol?
Thank you for a very nice talk. I have a question, mostly it's a comment maybe.
Okay.
Kaucher-Birkard is doing similar calculations in birational geometry, and he delivered a talk a few days ago claiming comparison with your work.
Okay.
And he said he obtains a bound which is much higher, and he said it's because he still has to refine it. Okay, so you have more assumptions. You put more assumptions in place. That's why you get a lower bound. So he's also expecting to get similar results as yours. But I was wondering, for cases like lower dimensional and lower supersymmetric cases, would it be that maybe you would have to look at the techniques that they're developing in birational geometry to maybe get some hint on the physics side and then develop that in turn?
Yeah, it's a very good idea. So I don't know how they work on this geometry, but if we can develop such technique from the geometry, we can borrow it to study, for example, as you said, the lower dimensional and lower
Yes,
space
exactly.
measure.
This is what I'm saying.
This is a very good idea. Yeah,
Okay,
thank you.
okay, thanks.
I just want to clarify an assumption to make sure I'm understanding. Is it an assumption of the argument that the string charge lattice is filled out completely by BPS strings?
No, we didn't assume it. Here, we didn't use such completeness argument. We don't know. There is no concrete low energy effective field theory argument that all the BPS charges must be occupied. But here, we didn't assume it. Yeah, we just derived that there must be H string. So this is without any assumption. Yeah.
Any other questions? If not, let's thank Hee-Cheol again. So our last speaker for today is Masahito Yamazaki, who is going to tell us about the work.
Okay. So while the slide is coming up, like other speakers, it's very much a pleasure for me to thank the organizers for this fantastic event. And also, well, I'd like to add that it's also very much a pleasure for me to keep coming back to the Strings Conference. And we heard that the Strings Conference seems to be going on for 35 years or so. And I'm not that senior, but I counted, and the first time I came to Strings Conference was 2008. Don't calculate my age. And then, and then each time there are new developments, which I enjoy very much. But on the other hand, it's also true that looking back some of the slides and all that, some fundamental questions remain. And in that respect, I recently came across a proverb in lab, which I hope is correct, which says that patience is the key to relief. And in this spirit, in thinking about this talk, I thought I should talk about some topic which have been keep coming back over and over since I was a graduate student. And I asked myself, what is the topic? And to me, that topic is the counting of BPS states. And I know this is a very diverse conference, but I hope everybody agrees that the counting of BPS states is a very important question. For example, it gives an ingredient to do very precise tests of dualities in string series and gauge theory, for example. And it gives a microstates of black holes. And also, from purely mathematical viewpoint, it gives a lot of beautiful mathematical structure concerning the enumerative invariance of the geometry, and so on and so on. So there are a lot of motivations. And in this respect, I'm very happy to report that about our new work in this direction, which is in collaboration with Jiakan Bao, who is an excellent postdoc at my institute, and that will appear tonight. So if you want to look at the details, please wait several hours, and we will find all the details, formulas, and everything. And then what I'm going to tell you is partly based on some earlier works. Well, the most recent one is with the Lakjun Song, but also a series of many, many papers together with collaborators, including Dima Garakov, Pei, Hiroshi Oguri, and many other people. So what is the setup? The setup is to compute, we start with Quiver gauge series, or with at least 2 supercharges. And I'm going to compute some partition function, essentially BPS with indices or elliptic genuses, and those are the quantities. So the series I'm going to consider is actually very, very, very general, at least by my standard. And for example, this is the example. Well, this looks like a 1D quiver, but the quiver can be more crazy. And with the 4 supercharges. So you can think of them as a dimension reduction of the 4D n = 1 series with the F-term constraints. Well, there could be more even reduced supersymmetry. In this case, there's a unoriented arrow, which is represented by color red here, which is called a Furby multiplet. So these are very, very general setup of Quiver gauge series. And then what is the result? So before coming to the detail, here is the main result. So the first is that you have to compute them, right? So VPS index, so there's the numbers. And there's a set of numbers, so there are infinite set of numbers. And the first question is that, what are they? Give me the number. Is it 10 or 12 or minus 13? And then the first result says that you can, there is a formula. So this is the generating function of all these VPS invariants. And it's given by some statistical mechanical crystal melting, which is defined as some statistical mechanism. So it's a sum of states. Sum of states we call the crystal state. And there's a weight associated with it. And the point is all these ingredients can be computed purely combinatorial. There's already a formula. Whatever quiver you give me, modulo some caveat which I'm coming to, there is a formula which you can write down. You can put it on computer. Now, the second result is concerning the algebra. So if you do the computation, you get a lot of numbers. But at some point, you begin to ask, is there any structure? Is there a complicated set of numbers? Is there any structure? And probably there are many different ways of answering that question. But one particular way of answering that question is that, is it a character of some algebra? So, and then the second result says that this VPS partition function, which is also crystal partition function, is a character of some algebra. Of Anderson representation R. So, so what is the algebra? Well, it turns out you can construct the algebra, which is a new algebra, which was not known in the literature. And for the reason which I don't explain too much, we are going to call it a double quiver algebra, because it's some sort of a double of the previously defined algebra. So these are the main points. So let me first explain a little bit more detail of what I mean by counting. So let's see. So of course, the counting problem itself is clear, and then we need some guideline, right? So if you want to compute things, and I have two guidelines in this respect. The first guideline is that for some geometries, this has been computed before, and those are the quiver gauge series corresponding to toric geometries. There is a torus action in the Calabi-Yau. Toric Calabi-Yau 3 and then the Calabi-Yau 4-fold. And so in the case of C3, there's this celebrated work by Okunko, Freshikin, Buffer, which led to the original model of the crystal melting. And for toric Calabi-Yau 3, in a paper with Hiroshi, we generalized it to more arbitrary toric Calabi-Yau 3. And coming back to that, and we recently had a paper about the toric Calabi-Yau 4-fold case. And in this case, the crystal in question is four-dimensional. So I cannot even draw it. So this is not a crystal, but just a figure of quiver. But the point is that regardless of the details, the answer is already known in some specific examples. So you expect that maybe something similar might emerge in a more general situation. Now, the second point is that, in a sense, the index has already been computed in a sense. And that's this celebrated JK residue formula. Well, so I know that this is the very end of a long day. So I'm not going to go into all the technical ingredients of this JK residue formula. But let me recap some of the very minimal ingredient of this formula. Well, first of all, this is a multidimensional integral. So we have to do multidimensional complex analysis. It's complicated. But at least under some assumptions, you can evaluate it iteratively. So if there are n variables, you just keep evaluating one by one. So it becomes an iterative integral. So it becomes a little bit more tractable. Now, the second ingredient is there is this eta parameter, which is eta in the literature. Well, technically, it's a duo of the Cartan, etc. Well, the rough physical meaning is that it separates the particle from antiparticle. So we are doing the BPS state counting. So you need to choose a cone and then count the BPS particles. And which cone to choose, that's dictated by this eta. Well, in practice, for the most of my talk, I'm going to choose a very particular eta. Now, there are extra ingredients. For example, the partition function depends on this set of parameters, epsilon, which is the chemical potentials. So if there are flavor symmetry in the theory, you can turn on the chemical potentials. And the residue itself is evaluated at the special points. These are singular points. And then of what? So singular points of the one-loop determinant. So this is the integrand and the singularities. And you take a roughly a set of residues there and sum over. And which sum to take, that's determined by this parameter eta. So that is already a known formula. Now the basic idea is extremely simple. So there's already a formula. And so that means that if you stare at this for a long time, it really looks like this is similar to the structure I was talking about. So maybe you want to regard this sum as a sum over the so-called crystal. So you define the crystal from this data, and there's going to be a residue from there, and that's going to be the Boltzmann weight. So that's a very basic idea. And well, probably many of you have heard about the Nekrasov partition function for instant counting. And Nikita derived his formula by using essentially this type of logic. In his case, that was 8 supercharges. But I'm discussing much more general class of theory with much more reduced supersymmetries. So, well, let me try to explain even a little bit more detail. So, well, first of all, I need to look into what this function is in order to discuss the pole structure. So, well, of course, that depends on what matter content you have. But suppose that there is a bifundamental arrow in between, the bifundamental matter. And then there is a one-loop determinant which contributes this factor 1 over zeta. And the zeta, well, depending on whether you want to do elliptic genus or width index or zero-dimensional matrix integral, there are a couple of functions which correspond to elliptic trigonometric rational hierarchy, which often appears in these type of topics. But let's say you are interested in the rational case, and zeta z itself is z. And then so this is just 1 over some function, which generates the pole. Pole with these parameters, which takes values in the Cartan of the gauge group. So it's very simple. You have a very concrete function, you can look at the poles. Now, let's look at this example. So there's a box represents a Flavor symmetry, and then there is a gauge symmetry. This is a very simple quiver with 4 supercharges. And then I'm going to evaluate it using these functions. And for each arrow, there's a set of functions like this. And this contains many, many poles. But suppose that, for example, when you evaluate the first variable, you take a pole from here in this arrow. And in the second step, you take a pole from here. That corresponds to an arrow going around here, a joint arrow. And then you can keep going. For example, there's a third step, you also take a pole from here. And if you evaluate it, the value of this u star, the variable, becomes the b1 plus epsilon1 to epsilon2, where epsilon1 is the parameter for this arrow. And then you can just plot it on this plane. And then what you get is that you just have a vertex, and it keeps going. So epsilon1, and then twice, 3 times, it just keeps going. And that's the picture you have. And well, if you just look at the pole structure of the previous expression, the actually poles correspond to going backwards too, minus epsilon1. But they're not taken under this particular choice of eta. So very roughly, intuitively speaking, the positive direction corresponds to a particle, but the other direction corresponds to antiparticle. So we are not taking it. So we get just the one-dimensional structure. Now, this is the simplest example, but you can keep doing this for many other examples. For example, this is an example corresponds to some affine Dinky diagram. It doesn't have to be this theory, but say, for example, this theory. And in the first step, you start from there, this blue box, and you go there. Second step, there are many possibilities. And then I plot them according to the charges. So each of the arrow has the charges, and then depending on that, it points in a specific direction. And going to the third step, and then going to the fourth step, it becomes more complicated, more possibilities. But then I can collect all these ingredients into the single graph, which is this graph. So in this case, it's a 2-dimensional picture with a lot of arrows and connectivity in between. So the statement is that since we are looking at the JK residue, this counts the combinatorial structure. So this counts the BPS states. Well, so if you look at the final result and then want to remember how to get the BPS states, you can basically start with the initial atom. For example, in this case, there is a lead bot, and then starting from there, going around the arrow, and then take some subset. And so we are calling it a molecule. So each of these vertices are called atoms, and then there you construct a molecule out of it. And if it satisfies some conditions, it's a BPS and include it. So you can write down precise combinatorial rule which matches the predictions or the result of the computation from the JK residue. And we are talking about a specific example. But we can come up with a precise rule which applies to n equal 4 as well as n equal 2 supercharged examples. Now, there is one thing to notice. So everything so far is more or less combinatorial. But of course, you might have to worry a little bit, because, for example, there are clearly examples where supersymmetry is broken. In which case, what I'm discussing this doesn't make sense. And at least there are some counterpart of that. So here, in evaluating the residue, we use the iterative formula. And then there is a subtlety of the JK residue. And very roughly speaking, it's not precise, but whenever higher order poles appear, there are some subtleties in the evaluation of the residue. So in an evaluation of the formula like this, we need to assume that that doesn't happen. So that restricts the class of series. So we still have to discuss a gigantic class of series, but not all the series, so that we don't run into contradiction. So this is the counting part of the story. Now, let's come to the algebra part of the story. What is the algebra we get? And here, there is no general result known. So we have to be a little bit hands-on and then try to construct the algebra. But of course, the algebra is going to be complicated, so we need some guidelines again. And then the guideline again comes from toric-Calabi manifold. So if you start with the quiver gauge theory with 4 supercharges, and then suppose that these quivers come from toric-Calabi threefolds, and in this case, the algebra is known by the name of quiver algebra. So in order to compare with the double quiver algebra, I might even call it a single quiver algebra, so that's a different algebra. So there was a single quiver algebra defined already in the literature. And then there, at least for toric-Calabi 3, with 4 supercharges, a similar story existed already. Namely, there is an algebra, and then the crystals, and action on that, such that the partition function is the character of that. And then this quiver algebra itself is a well-defined algebra with some generator and relations. And it's a complicated algebra, but it has a known connection to other topics, like affine Yang-Yang quantum toroidal. And you can even truncate it, get corner VOA, all the way to WN algebra or Virasoro, etc. So it's just a bus generalization of Virasoro in a sense. Well, and of course, the natural choice is that maybe you can try to start with this algebra and then try to act on the crystal I just constructed. That's what I've been doing for a long time. But apparently, there's some obstruction for doing that. So instead, I decided to change the algebra. So I decided to start with the quiver algebra, original one, but then change it to a new algebra, which we call the double quiver algebra. And well, of course, this has a more precise meaning. But my at least vague intuition is that it's like here in this original algebra, we included the generator for particles only. But here, I include a generator for both particles and antiparticles. And then, of course, there are many more poles. We are not including everything, so we need to do something to take care of the extra poles. So that's more or less the main idea. So, OK, what is the double quiver algebra? Well, it's defined by generators and relations. So the generators are, we have a set of generators for each vertex of the quiver. So we have a nodes. For each vertex of the quiver, we have a generator, E, F, psi, omega. And so E and F, E, F, psi, these are like a Shubari generators, as we will see. So E is like an upper triangular part, F is a lower triangular part, psi is a Cartan. Now, compared with the previous quiver Yang-Yang, single quiver Yang-Yang, we are including an extra generator, which also plays an important role. And in order to write down the relations, I introduced some function. The details doesn't matter, but it's written in terms of the zeta, which I introduced previously. For the rational case, zeta z is simply z. And then I can write down the relations. So despite the fact that this is the very last talk of the day, this might be one of the most complicated formulas you've seen today. But please don't be discouraged, because actually the relation hasn't ended. So there is even one more page. But the main point is that there are relations. And OK, so these are like somewhat like OP type relations you're familiar with in conformal field theory. So these are, each of these generators has a parameter dependent, spectral parameter. You can expand, and then there are infinite, it contains infinitely many generators, actually. And so some of the things commute. For example, in the first equations commute. But in other cases, don't. And there are a couple factors like this. And there's a psi tilde. Psi tilde is this gigantic beast. It might not be too elementary if you just stare at it. But the point is that everything is very explicit, which is good for, especially if you're a physicist. I say that because there are some construction of some similar algebras in mathematical literature. But quite often, sometimes things are very abstract. So the important thing is that you can write down everything explicitly at least. And then in this algebra, we haven't done too much. But if you like, you can try to keep truncating to make it something simple. And one comment is that this is not associated with any Lie algebra or anything. It's more like associated with the Quiver. So there are all sorts of algebras known in the mathematical literature, quantum groups, quantum affine, etc. But all of them are associated with the Lie algebras and deformations. But this is not. And so now we have the algebra. We can go back to the crystal, which we constructed before, and try to let it act. And this is the type of formula you found. So there are Shubari-like generators. They act by creating annihilation operators. So these are like creation annihilation operators. So remember that we constructed crystal by adding atoms one by one. So these create annihilate atoms. And some of the generators act diagonally. But now this omega takes care of the poles which are not allowed by eta. So these are like antiparticle contributions. And then finally, all these factors here. All these factors psi tilde. And I'm not going to write on the formula, but the important part is that this is also determined by the one-loop determinants of the JK residue formula. So this itself counts. It seems that this itself contains only the BPS, the information of the crystal. And in the BPS state counting, there is also weight associated with it. Namely, each crystal state represents a combination of BPS states. And that information is contained in these weights. So it seems to capture all the information of the BPS state counting, but in a somewhat asymmetric way. So this was a little bit more details. And so let me try to summarize. So the statement is that starting with the very general data of Quiver gauge theory with two supercharges, and together with the, in that case, relations, J terms and E terms, I constructed the model of crystal melting. It's a statistical mechanical model with a very precise combinatorics. And then also, as well as the new algebra, which we call the double Quiver algebra. And this double Quiver algebra is it acts on this crystal state. So it's a version of the BPS algebra, BPS state algebra, so-called in the literature. Now, this story, of course, works with n=4 quivers as a special case. And in that case, there was already, and when this comes from Tori-Carabiao, there was a different algebra, Quiver BPS algebra, single Quiver algebra. So I'm writing down two different algebras, and which is a little bit somewhat confusing. But it turns out that neither one contains the other. But if you extend this thing a little bit, then both of these things are included. So the relation is a little bit subtle. But at least that seems to be related to the fact that here, compared with the typical case, I'm turning on extra fugacity for this counting. And then somehow, at least the rough intuition I said is that this one, double Quiver algebra, counts both the particles and antiparticles. Now, now we have the new algebras and representations. And so hopefully, that will interest mathematicians too. But this is a conference about the string theory, so you can ask, where is string theory? well, of course, it's a version of BPS state counting. In some contexts, you can discuss the models of BPS black holes, which is non-compact, et cetera, et cetera. But in this respect, I should say that one of the motivations come from partly the paper by Kamran, and others about, so we are trying to, the original motivation for this paper is that these crystals represents the so-called quantum form. So typically in string theory, we begin to see the stringy collection at some point. But in this context, we want to see more like a quantum aspect of the geometry. And the atoms I'm talking about, it turns out it's more like atoms of the space-time. So namely, we start with the atoms, and then we combine them together, and take a sample limit, and they're going to see the smooth geometry, as in this figure. So in a sense, the smooth geometry, it looks like a smooth geometry, but if you go into the quantum regime, there is something popping up. So that was the main motivation for this. And this whole story of the crystal melting makes it precise. And first of all, this story generalizes to the less supercharged, more general stories, and then that's one lesson from what I said. But of course, now I have a more precise algebra and everything. Well, okay, in a larger, I have a precise algebra in larger context. So you can ask, what type of lessons we can learn from this? And the short answer is that I don't know. But I just have some very preliminary comment. So which is about how the atoms fit together. So in the typical story I was presenting, and in the old work, including my old paper with Hiroshi, we are talking about the crystal melting in such a way that whenever you have a so-called molecule, everything can be constructed out of the atoms. So what I mean is that I have something complicated, but I can take atoms one by one. Or if you go backwards, you can try to construct everything starting from single atoms and bring it one by one. And each action of the bringing it in or bringing out is represented by action of the generator. So that is the story, and it's kind of nice. Everything is like a molecule, and there is an action of the algebra which represents decomposition into the atoms. So, but we found that that structure is not always true. For example, there was a eta parameter which didn't play prominent role in my talk so far, but I changed to a different eta. And there, it happens. Sometimes you cannot create a single atom. You cannot create a single atom. You cannot add a single atom. But it is possible to two atoms simultaneously. And whether this happens or not depends on this extra data, which is called the eta. And then so this is somewhat, I'm tempted to call it speculatively that this is more like a confinement mechanism of space-time form, in the sense that in some cases, you can create two, but only with two together. So this is one of the small examples of the lessons we might be able to learn from the algebraic structure. And this is only a small starting point, and I'm not sure what will come out. But there is a general question of if we get something extract some statement like this, is there any general lessons we can learn about the quantum gravity out of this? That's one of the future questions. And as I said at the beginning, we have to be patient. So it might take some time. But I'm optimistic that we will eventually make some further progress along those lines. Thank you so much.
Any questions for Masahito?
Historically, space-time firm has been the name given to some special types of metrics which look like these vacuum bubbles. Mm-hmm. Are there any metrics or geometries that you're associating to these?
Well, let's see. So these are, so these are more like if you have, in the original context, you have a geometry, and then you kind of geometric quantization, and then it discretizes it really. So it's not a particular metric associated with this particular point, I would say. So in a sense, the concept of metric, well, at least, well, of course, I don't really know the eventual understanding. But my idea is that it's not like there is a geometry. There is no geometry in a sense. And the geometry self-emerges. And these are some basic ingredients out of which the geometry is constructed. So in that sense, there is no metric. Sure. Yeah, so it resonates well a little bit of the idea that the gravity is emergent in one way or another, yes.
Any other questions? I have one question. So in the case with two supercharges,
yes,
in these formalism that you develop, what are the particular applications that you have considered in string theory. So this would be with theories in lower than 4 dimensions?
Yeah, I think that could be the target. For example, this algebra applies to Calabi-Yau four-fold compact creation, for example. And some of the nice stories go away, but at least it's an honest BPS state counting for Calabi-Yau four-folds, toric Calabi-Yau 4, for example. Or it doesn't have to be toric, but sorry, it could be other Calabi-Yau 4. And then, so what lessons we extract out of there is not clear, but we can try to, for example, study the asymptotics, and it might be a version of a black hole, for example.
And you can use these to find duality or check dualities and so forth in your...
Yeah, I think, it's a more subtle question. For example, there are some quivers which are dual, like a Seibach duo or the triality, etc. And you can ask the question if the algebra is preserved, for example. So the algebra, first of all, the counting is the same. At least, there's a modular dependent wall crossing, etc. But as long as it's corresponding chamber, the counting itself coincides. Now, you can ask if the algebra acting on that are the same. And in some cases, we conjecture that they're the same, but there are some other evidence that in general, the algebra might be different. So algebra might be different, but the counting is the same. And, but that's, so that's probably related to the picture of, basically the basic degrees of freedom different when you have a duality, right? So, so these generators of the algebra represent what are the basic degrees of freedom. Basic degrees of freedom, whenever the basic particle, you prepare a generator and then construct everything. That's the idea. So so in that sense, you have to reshuffle the generators one to the other. That's the idea. So it could be that maybe if you suitably kind of confine the algebra, modulo gauge equivalence class or something, and then maybe these two algebras might be equivalent, but not among themselves.
I see. Any other questions for Masahito? If not, let's thank Masahito again for a wonderful talk.
Thank you.
Before we leave, there's an announcement.
Just to let you know that the bosses are waiting for us outside to go for the gala dinner. So I think they are just waiting and we leave immediately. We can go now, yes.